So, what I want to talk to you today about is why we're not here yet. 40 years after we've been to the moon, we thought we'd be on Mars like in the 1980s or something like that, and we're totally not on Mars yet. So, the short answer is we're not on Mars because it's really expensive. It's really expensive because it's hard. And not only is flying to Mars hard, understanding why it's hard to fly to Mars is hard. It really does take a rocket scientist. This is Robert Goddard. So my goal in the next 40 minutes or so is to turn all of you who are not rocket scientists already into rocket scientists. We're going to do this in 3 easy steps. We're going to start with what we know and love well here at Johnson Space Center, low Earth orbit, talk about the moon, which we did 40 years ago, and then extend that to what it takes to go to Mars. So starting off in low Earth orbit. There's our favorite object in low Earth orbit, the International Space Station, which they're busy operating over here just a couple yards to the south of us. I also need to point out here the best module on the space station right there. The shiny one there, that's the Columbus lab that my crewmates and I put up totally unbiased. Remember that the space station orbits the Earth only about 250 miles up. And that's not very far into space, especially when you compare it with the size of the Earth. The Earth is a ball about 8,000 miles in diameter. 250 miles up is just barely above the top of the atmosphere. And that is the only place we could have put the space station. If we put it any lower, the air would have been dense enough to bring it down through air drag. If we tried to put it any higher, the space shuttle wouldn't have been able to carry those heavy payloads up that high to build the space station there. So that was our only option, about 250 miles up, to put the space station. Now remember, the space station is in orbit, and I want to talk for just a minute about what that means, because most people don't know. I think in this room we're probably pretty safe, but bear with me. So this picture is actually from the Principia by Isaac Newton, in which he invented the concept. And his thought experiment was to have a really tall mountain here that is higher than the atmosphere, so you don't have to worry about air drag. You put a cannon on top of the mountain, and you fire cannonballs out of the cannon at various speeds. And we all know what happens when you shoot a cannonball out of a cannon. It flies a little ways, and then its path curves under gravity until it comes down and hits the ground. And that's illustrated here by this line that ends in the letter D. So Newton's thought was, let's put a little bit more gunpowder in the cannon and fire the cannonball out at a higher speed. And now maybe it will come flying around, but it still curves down toward the ground, but it goes further and maybe gets to point E. And we'll load a little more gunpowder in, and we'll fire the cannon again. And this time we get a good head of speed. The cannonball flies a long way before it finally hits the ground there at point F. But you can see what's happening. As we increase the speed of that cannonball, it keeps curving toward the Earth so that it's going to hit the ground. But when you get out to point F here, the Earth's surface has curved away from the cannonball quite a bit, and it flies a lot farther. Finally, we load enough gunpowder into the cannon and fire that cannonball, it will come flying all the way around the world, and it's still feeling plenty of gravity. See all these pictures of the astronauts floating around in the space station. It looks like, oh, there's no gravity. Nonsense. There's oodles of gravity up there. If you built a tower 250 miles tall and stood on it, of course you'd need a spacesuit because there's no air up there, you'd feel something like 90% of the gravity that you feel in this room. You would be pulled down very solidly onto the top of that tower. The reason the astronauts don't feel the gravity is because they're falling, and they can fall for weeks and months at a time because their forward speed is so great that even though their path is curving toward the Earth's surface under gravity, the surface of the Earth is curving away from them at the same rate, and they never hit the ground. That is what it means to be in orbit. You're going forward so fast that even though you're falling toward the ground is curving away from you and you never hit it. And that's also the hard part about getting into space. Getting up into space is not hard. The Germans were doing it in 1942, sending things to Antwerp and London. Okay? Up isn't the problem. The problem is going forward fast enough so that when you get up into space, you stay there. And that speed, once you allow for the fact that your rocket has to go uphill and in a headwind to get up through the atmosphere and get into space, is about 20,000 miles per hour. And let's see, for this audience, I should be using feet per second. For For general audiences, though, miles per hour. And for all the scientists, I apologize for not using metric. But if I use metric, everybody's eyes roll up and the message gets lost. So we're gonna stick with miles an hour here in the interest of our folks with less science education. Right. A reminder about the harsh reality of launching. Mother Nature is an extremely tough grader. So every time you push the button to launch a rocket, you are signing up for a situation where if you get 99% of the way there, 99% of your 20,000 miles per hour, that's a launch failure. That means debris coming down in places and possibly funerals. Okay? So 99 out of 100 is a failure. That's what we're signing up for every time we burn a rocket engine to go to orbit or, in fact, anywhere else. All right, we've all seen TV and the movies, and they make space travel look really easy. You just say engage or make it so, or, you know, ahead warp factor 6, Mr. Sulu, and it happens. But unfortunately, we are not quite there yet from a technical standpoint. So instead of using things that look like this, we have to use things that look like this. This is our space shuttle. It looks like, when you see a picture of the shuttle stack, you have this big airplane thing, and then a big tank that's kind of about the same size as the airplane, and then two skinny rockets that are smaller than the airplane. But size is deceiving. When this critter is sitting on the pad, the airplane weighs about 100 tons. Each of these white rocket boosters weighs about 630 tons, 6 times as much as the airplane. That tank full of propellant weighs something like 840 tons, 8 times the mass of the airplane. This thing is an eggshell. These things are heavy and full of propellant. That is the only thing that makes it to orbit. So the heart and soul of this system is the Space Shuttle main engine. This is one in the test stand back at Stennis Space Center in Mississippi. And although it has been joked that prediction is hard, particularly about the future, I'm going to come out and say, not only is this the best chemical rocket engine ever made, it may be the best chemical rocket engine that ever will be made. And I want to take a moment to explain that statement. The thing that determines how much boost you get out of a rocket engine per unit mass of fuel you put into it is a parameter called specific impulse. Specific impulse is just another way of measuring the exhaust speed of the gases coming out that nozzle. So if you want to get a long ways with a little bit of fuel, you need a really good specific impulse in your engine. Specific impulse then, just measuring the exhaust speed, depends on 2 things. It depends on the temperature of the gas coming out of that nozzle. Higher temperature means faster speeds and better specific impulse. And it depends on the molecular weight of the gas. Lighter gases give higher exhaust speed and better specific impulse. So those are the 2 things we would need to mess with to get a better specific impulse out of a chemical rocket engine. Let's talk about temperature first. This is actually a flame. It's transparent because it's so hot. The temperature in that flame is something like 5,000 degrees Fahrenheit. And there is nothing on Earth that can withstand that temperature without melting. Period, end of sentence. This nozzle is made out of a high temperature alloy. It would melt in a flash if it didn't also have about 1,100 little tubes in the outer wall that are running the ultra-cold liquid hydrogen propellant that's going to be burned in the engines through that wall, that nozzle, to cool it, and then that gas gets sent off to the turbopumps to get burned in the engine. So we need an actively cryogenically cooled engine made out of the highest temperature materials that we have just to withstand the flame temperature in this engine. We can't really make the exhaust any hotter because we'll slag the motor. All right, so then the other thing we can mess with to get better specific impulse is the molecular weight of the gas. Space Shuttle main engine burns hydrogen. To burn anything, you need to combine it with oxygen, so we're stuck with oxygen, although asterisk fine print, I have read that if you really don't care about your neighbors, you can replace the oxygen in any rocket engine with fluorine. And you can get a few more seconds of ISP out of that, maybe a 1 or 2% boost in the fuel economy. But then you leave this big trail of, instead of hydrogen oxide, which is water, you leave hydrogen fluoride, which is hydrofluoric acid. And that etches glass. And anyway, the environmental impact statement is beyond what we wanted to do. And the performance gain isn't that great. So let's just say we're stuck with oxygen. Fluorine doesn't help you that much. Our fuel is hydrogen. That's the lightest element in the periodic chart, and we are quite confident that we have thoroughly explored the periodic table of the element, and we are not going to find any elements lighter than hydrogen. So our two parameters that we can mess with to get more performance out of this engine: temperature, molecular weight, and we're stuck. We're at the limits of what the materials available to us and all the clever engineering that we can do with those materials will provide. So I don't think we're going to do better than this with chemical engines. If you're not using chemical engines, then we have a different story, but we'll talk about that later. So despite those limitations, despite having to carry many times more fuel than your payload weighs, we did use chemical engines 40 years ago to get to the moon. So let's talk about that for a few minutes. So here's our Earth, 8,000 miles across. Now we're going to pull the camera back. We're going to back up and back up and back up until you can see this little gray dot there, and that's the moon. And this picture is to scale. So it's the Earth and moon at their correct relative sizes and the correct relative spacing between them. It's about 30 Earth diameters between the Earth and the moon. And that distance, as we all know well here at JSC, is about 250,000 miles. And if you take off 3 zeros, you get approximately the distance of the space station from Earth. So the moon's about 1,000 times further out into space than the space station is. But the problem is not the distance. The problem is the speed. Let's talk about the speed you need to get to the moon and back. So we're going to launch into low Earth orbit, which takes 20,000 miles per hour. Remember, if we get 99% of the way there, we drop wreckage all over Africa or Europe or something. We don't want to do that. Takes another 8,200 miles per hour once you're in low Earth orbit to break out of low Earth orbit and head to the moon. If you only get 8,000 miles per hour, you get in a high Earth orbit and you come right back and you never make it to the moon. That's embarrassing. You have to explain that later. Once you approach the moon, you have to do a burn of about 2,400 miles per hour to drop into orbit around the moon. Otherwise, you just fly past the moon, and if you're lucky, you come back to Earth the way Apollo 13 did. If you're unlucky, you get kicked out into orbit around the sun, or you never come back, and that's bad. So it's very important to complete that burn. Once in low lunar orbit, you need to kill off your forward speed in orbit around the moon so that you can come down to the surface. That takes a burn of about 3,900 miles per hour. As you approach the surface, you don't really want to hit at orbital speed, nor do you want to drop from orbital height. You need to expend some gas to hover and land softly. And that takes about 700 miles per hour. And I didn't have a picture of that because, of course, there was nobody pointing a camera at the lander as it was landing on the moon. But this is the lunar lander trainer being flown out at Ellington Field. One of these actually had a malfunction in flight, and Neil Armstrong had to bail out of it. It crashed, and he landed safely on his parachute. And there's one of these hanging up in the Teague Auditorium front hall. You should go take a look at it. Once you're there, you get to do all the fun stuff, and we don't have to burn any propellant. We can collect our samples, we can salute the flag, we can drive around the moon buggy, we can hit a golf ball. And it's time to come home. 700 mile per hour burn to lift off and support the weight of the spacecraft while you are re-attaining your orbital speed. Again, if you fail on this, you crash on the surface and perish. Another 3,900 miles per hour to regain lunar orbit speed, to put yourself in a nice circular orbit around the moon. If you fail in this, you crash on the surface and perish. You may notice a kind of a common theme here. Once you've achieved low lunar orbit, it takes another 2,400 miles per hour to break out of low lunar orbit and head back toward the Earth. If you fail in this, you're stuck in orbit around the moon until your supplies run out and you perish. Now we finally get a break. Coming back to the Earth's atmosphere, we can use the atmosphere to slow down. That's what the Space Shuttle did every time it returned from orbit. That's what Soyuz does every time. And that's what the Apollo capsules did, except they came in at a speed about 40% higher than the shuttle or Soyuz. The gas temperature in front of the spacecraft as it's doing its atmospheric entry was something like 18,000 degrees Fahrenheit. This is actually a photograph from the ground of an Apollo capsule coming in to the atmosphere on its way back from the moon. But you don't have to expend any propellant. You just have to carry a really good heat shield. And then finally, the Earth does have enough atmosphere that once you get low and slow, you can pop out a parachute and let the atmosphere gradually decelerate you, land in the water, and that doesn't take any propellant. So let's add it all up, and you get 42,000 miles per hour. That's a lot of speed. And we're doing it all with chemical rocket engines, and that is why of this 360-foot tall rocket that left the pad, what we got back was this little 10-foot cone. That little tiny thing up there on the top. The entire rest of that huge rocket is either propellant that we throw out the back or empty propellant tanks, which we throw away because we can't afford to carry their empty weight any further. We just can't take the propellant. That's like buying a Boeing 737 brand shiny new, flying it from Houston to San Antonio and scrapping it because you can't refill the tanks. So let's take a look at that little cone again. That thing weighed about 6 tons, and into that we had to put our 3 Brave Explorers. The equivalent of about 33 scuba cylinders full of oxygen for them to breathe. That's 3 guys for a week. They carried liquid oxygen, so they didn't actually carry it in pressurized gas form. It takes up less room as a liquid. 3 people for a week is going to drink up about 4 of those great big plastic bottles you have in the water cooler for water, and about 1 cartload of groceries to keep them fed for a week. And all that fits into a 6-ton vehicle without too much trouble. All right, let's talk about Mars now. So this is where it gets difficult. Let's start with the speeds, the way we did for the moon. We're going to launch into low Earth orbit on our way to Mars. This is our SLS, Space Launch System rocket, that's under development right now in its heavy lift version, which should be able to put 130 tons in low Earth orbit, slightly bigger than the Saturn V that we used for the moon. Once in low Earth orbit, we're going to do a burn to send ourselves on the way to Mars. That's about 9,000 miles per hour. Notice that that's like 10% more speed than it took to go to the moon. 8,200 miles per hour to put yourself on course from low Earth orbit to the moon. Just 800 miles per hour more, and you're on your way to Mars. That's the advantage you get of doing an engine burn down deep in a gravity well. Little differences in speed down low make a big difference in your speed once you get high up away from the Earth. After a substantial period of cruise that we'll go into detail later, you arrive at Mars, and Mars does have enough of an atmosphere that if you carry a big heat shield, you can use the atmosphere to slow down. So you can slow down when you get to Mars without having to burn engines, and it doesn't cost you any propellant. Such a deal. However, Mars does not have enough atmosphere to land anything bigger than, say, one of the current Mars rovers on a parachute. The Mars rover that's going to arrive next month has to use a propulsive system to slow down because we couldn't pack in a parachute big enough to slow it down. And if you put people on board a spacecraft, it's going to be huge, and there's just not enough air there. So we're going to have to do a propulsive landing, which means supporting the weight of the spacecraft against the pull of Mars's gravity after you've slowed down from cosmic speed so that you can make a soft landing. And that's going to take you about 2,000 miles per hour because Mars's gravity is stronger than the moon's. Once you're there, you can have all your fun, drive around, collect your samples, make statements for your corporate sponsors. And then it's time to come home. A word on this. When we get ready to launch a vehicle out of Florida, there are thousands of dedicated workers down there at Kennedy Space Center who do all the preparations. They check the spacecraft out. They help the crew get in the capsule. They're busy for months to prepare for a proper launch. When you get to Mars and it's time to come home, you will do all of that yourself with no help. So the systems have to be really autonomous. They have to be very simple to work because you don't get any help when you're getting ready to launch off Mars. So 17,000 miles per hour is what it takes both to get off Mars and then the extra boost you need to send yourself on a course back to the Earth. And notice that that is almost what it took to get into low Earth orbit. So this is a lot of propellant. You're going to have a very big rocket and a very small capsule that makes the trip. After another lengthy cruise period, you return to the Earth, and the Earth has enough atmosphere to slow you down from cosmic speed. You're going to come into the atmosphere even faster than you did when you returned from the Moon, maybe an extra 10% faster. This means your heat shield has to have higher performance than a lunar heat shield, but we have brought capsule shapes into the Earth's atmosphere at those speeds before. The Stardust sample return canister, which was a little tiny Apollo capsule shape with a heat shield, came in at roughly Mars return speed, and it did all right. But that was a little tiny thing. We'll have to build a bigger one. The Orion space capsule, by the way, that we're developing right now is designed for Mars return. So they had that in mind, but the initial version of the heat shield won't be sized for Mars return speeds. But at least you don't have to spend any propellant to do it. And once again, Earth has an atmosphere that you can land softly on a parachute. This is an actual Orion capsule drop test. So we'll add them all up, and we get 48,000 miles per hour. Only about 20% more speed than it took to get to the Moon. That's hardly any difference at all. So how come 40 years after we went to the Moon, we can't get to Mars? And the answer is it's not the speed, it's the distance. So here's our picture of the Earth and Moon with 250,000 miles in between them. And let's pull the camera back one more time. And pull it back, pull it back, and pull it back. And now it's getting hard to see things, so I'm going to have to draw some extra stuff for you to look at. That dashed line is the circle that the Moon makes in its orbit around the Earth. The diameter of that circle, about 500,000 miles. The Moon is now much smaller than the dashes. You can't see it anymore. And the Earth is just a dot. And we'll back out the camera some more, and more, and more, and more, and more, until now even my circle of the Earth's orbit around the Moon's orbit around the Earth is tiny, and I'll have to draw you another landmark. So the big blue dashed circle is the orbit of the Earth around the Sun. The yellow dashed circle is the orbit of the planet Venus around the Sun. And at their closest approach, the planets are about 26 million miles apart. This happened just last month when Venus did a transit of the Sun. It was directly between the Earth and Sun. It was about 26 million miles away from us at that time. But we're not done pulling the camera out. Orbit of Mercury now coming into view, and the Sun coming into view. And we're going to pull out until finally, and I'm sorry that's hard to see, you can see this red circle, and that's the orbit of Mars. So those are the orbits of the 4 inner planets around the Sun. The planets themselves are invisibly tiny at this scale, and even the symbol for the Sun is artificially big, just so you can see where it is. So let's declutter the inner planets and put some scale on here. So the Earth is on average about 93 million miles from the Sun. It takes it 12 months to go around. Mars, on average, about 140 million miles from the Sun. It takes it 22.5 months to go around. And everything in the solar system circles around the Sun counterclockwise as seen from the north. So the direction of the arrows indicates the direction of motion of the planets. So that doesn't look too bad. Why don't we just wait until the planets line up where Mars is at its closest approach to Earth and fly there, like that. That's how you do it in the car, right? Well, you can plan that out, and it turns out that the speed you need is somewhere around 250,000 miles per hour. And once again, we have yet to develop warp drive. We can't do that. So instead, we're going to have to use what's called a transfer orbit. Our transfer orbit is an elliptical orbit around the Sun You can put anything on that orbit, and it will continue to orbit the sun until it hits something or gets kicked out of the solar system. In this case, our transfer orbit is at its closest point to the sun. It's as far from the sun as the Earth is. And at its furthest point from the sun, it's as far from the sun as the planet Mars is. I say, we just go ahead and put something on that orbit, and we'll continue to shuttle back and forth between the orbit of the Earth and the orbit of Mars forever. And it takes about 17 months for it to go around. And that is the orbit that we used when we calculated those speeds earlier. So this is our minimum energy trajectory to get to Mars. You could think about trying to go faster, but then you're wasting fuel, and wasting fuel means bigger than necessary tank, bigger than necessary rocket, and bigger than necessary budget. People are going to give you trouble for that. Another thing to remember about our transfer orbit. There are no boomerang flights when you go to Mars. Once you have done that burn to set yourself on the way to Mars, we can't carry enough propellant to turn around and come home if we decide we don't like the way things are going. Once you're on your way, you're committed. So, let's make it go here. Here's our map of the solar system. Sun in the center, orbit of the Earth, orbit of Mars, our transfer orbit in white. The dots, the blue dot represents the Earth. Remember, the Earth itself is invisibly tiny at this scale. Red dot represents Mars. The Mars itself is much too small to see. White dot represents our spacecraft, and of course it's way too tiny to see. So we will start, and we're going to count months down here and see how it goes. So we're going to launch off of Earth. We're going to give ourselves a little excess speed in orbit around the sun, so we pull away from the Earth leading it, and then that extra speed will carry us uphill out toward the orbit of Mars. As the months go by, 6, 7, 8 months, 8.5 months, we have arrived at the orbit of Mars. Unfortunately, the planet itself is 80 million miles away from us, behind in orbit. It's further away from us than when we started, and we're totally embarrassed. And we got to explain that later. But it gets worse. Remember, once we're launched, we're committed. We don't have the propellant to do anything different. We will continue in our orbit around the sun, just like an asteroid or comet, until 17 months after launch, we have arrived back at the orbit of the Earth. But unfortunately, the Earth itself is clear over on the other side of the sun, 160 million miles away. We're nowhere near it, and we're just going to keep going around the sun like an asteroid or comet until our supplies run out and we die. That didn't work out so well. So let's be smarter about our departure timing, shall we? So this time we're going to cleverly wait until the Earth is here in its orbit and Mars is 40 degrees or so ahead of the Earth in orbit. When the planets reach that relative alignment, that happens, by the way, about once every 26 months. Imagine two cars on a racetrack going around at different speeds. The Earth has a smaller circle to go around, and it travels faster in orbit than Mars. About every 26 months, they are in the right alignment to send something from the Earth to Mars. So we're going to be smart about our departure time. We'll launch out of Earth. We'll count the months just like before. We'll head out away from the sun on our transfer orbit. Once we get out toward the orbit of Mars, we're actually traveling slower than Mars in orbit, and it will catch up behind us. And ta-da! We made it. We have arrived at the orbit of Mars, which is not the same thing as Mars orbit. If you read the newspaper, you think, oh yeah, orbit of Mars, Mars orbit, same thing. No. Orbit of Mars, the circle around the sun. Mars orbit, that means you're going around Mars in orbit. We have arrived at the orbit of Mars at the same time and place that Mars itself is there. We have arrived at the planet. We plant the flag, we make our footprints, we thank our corporate sponsors, and off we go. Heading back in toward the orbit of Earth, and you can already tell that we're going to... All right, well, we solved problem number 1. We got to Mars, but the problem number 2, where we have arrived back at the orbit of the Earth, and the Earth itself is nowhere near us, and we're going to circle around the sun until our supplies run out and we perish. So that didn't work so well either. But third time pays for all. We'll try one more time here. We're going to launch off of Earth on our same transfer orbit. We'll time our launch so that we arrive at the orbit of Mars at the same time and place as the planet does. And 8.5 months later, we arrive. Now we land, and now we are going to wait for a good time to return to the Earth. Since on Mars we have at least 50% radiation protection, because when you're standing on the surface, you don't get radiation from underneath. You have an atmosphere you can work with. You have a lot of things you can do. It's a good place to wait compared to deep space. So we're going to wait on Mars for the planets to line up so that we can safely come back to Earth. And we're going to wait, and wait, and wait, and wait until almost 2 years after we left the Earth, the planets have come around to an orientation where we can get back. So we'll launch off of Mars onto the same transfer orbit, except rotated around now, so that it connects where Mars is when we left with where Earth will be when we get there. We come falling in toward the sun. When we get close to the Earth, we catch up to it from behind. And finally, 32 months after we left, we return safely. 32 months. That's like 3 years. So, we're going to spend 3 years in space. Into our spacecraft, which we have yet to design, we're going to put our intrepid crew. This is the crew of the Mars 500 simulation that was recently done in Russia. 6 people. The psych folks tell us that 6 would be a good number to send to Mars, because if you get fewer than that, you can get conflicts. You know, don't send 3 because 2 will gang up on 1. Don't send 2 because 2 will gang up on 2. 6 is good. And you can't send less than 4 because the international partners won't sign up unless their people get to go. And we need international cooperation to be able to afford this. So 6 is a good number. Now, in 32 months, 6 people are going to breathe up about 9,000 scuba cylinders, about 1,100 big bottles of water. You know, one of those bottles weighs 40 pounds, so 40,000 pounds, that's 20 tons of water, and 280 carts full of groceries. I would not advise bringing the bananas. After 32 months, they're not going to be appetizing anymore. So that's a lot of supplies. But it turns out we have a spacecraft that is sized properly for that big a crew and about that amount of supplies, and it's called the International Space Station. It's in orbit right now. It weighs about 420 tons. And just as a reminder, to build that took 27 of those, 2 of those, that's a Proton, and 2 of those, that's a Soyuz. That's just to bring the parts up. That has nothing to do with the crew rotations, the resupplies, and all the other things that had to happen while we were building and have been operating the space station. So it takes all that to build a spacecraft that size. So that's kind of big, and we'd like to make it smaller. And there's a couple of ways that we can do that we're investigating right now on the International Space Station. The first is to try to recycle things, especially that water. You're always exhaling water with every breath, and it's water vapor. You can condense that and basically get distilled water, which you can drink again. You're also producing water in other ways, which are also being recycled on the space station, as my friend Mike Fink says, we're turning yesterday's coffee into tomorrow's coffee on board the International Space Station. So recycling is a great way to do this. And we have machines on the station that can distill condensate and wastewater to make drinkable water. They can also take water that's not drinkable but still pure enough to do chemical reactions on and split that into oxygen and hydrogen. They can bring the oxygen back into the cabin, vent the hydrogen overboard, and start to recycle some of the materials that we're using. Although, truth be told, those systems are not our most reliable. The recycling systems belong to the Environmental Control and Life Support Systems Group, or ECLS. And together they're called the Regen ECLS system. The thermal engineers who are helping to operate the space station put out this joke a couple of years ago, which was a joke copy of the space station warning board that's in mission control. It tells all the current malfunctions on board the space station. Usually it's clear, thank goodness. But it said, warning, Regen ECLS not failed. So they were poking fun at the ECLI. It's not for any lack of work. It's just the first time we've ever tried to build a closed environmental life support system like this, and it's hard to do. But we're working hard on it. A related problem, if you're on your way to Mars, you cannot get resupply, and things must not break. Things do break on the space station. I mentioned on our shuttle flight, we brought back a control moment gyroscope, one of the big heavy gyroscopes the station uses to orient itself in space. One of those had broken. We brought it back to be refurbished and then flown back so that it can be used as a spare. Things do break, but we need to make huge improvements in our reliability of all the systems in a spacecraft if we're going to be able to get to Mars and back. And again, we do have a platform to practice all that, and it's orbiting the Earth right now, and we're working on these problems. So we think if we're very careful about sparing, oh, and one other thing I should mention, the last few shuttle flights to visit the space station carried nothing but spare parts to be placed up there because we knew we weren't going to get any more shuttle flights. And so several flights worth of payload were just spares. We think if we're very good about reliability, we can keep the number of spares down. We think if we're very good about recycling and don't have to carry fresh air and fresh water, can recycle those things, we might be able to get the spacecraft down to about 100 tons. And for you sticklers out in the audience, that's the mass that completes the trans-Earth injection burn. We're probably going to leave parts all the way there and all the way back, just like we did for the moon. Still, 100 tons, let's review for a moment. Back in Apollo, we had a 6-ton capsule. And it launched on a booster that weighed 3,350 tons when it was sitting on the pad. For our 100-ton spacecraft, our mass sitting on the pad is going to be something like 85,000 tons. So that's the same mass ratio for Apollo, but boosted up a little bit because the speed requirement to get to Mars and back is a little bit higher. So that's not so bad. We have ships that weigh 85,000 tons. Except, the Avengers notwithstanding, they do not fly. So 85,000 tons, and just to put that into space terms for you, that would be 39 of those, or 25 of those. Now, we think we might be able to get those numbers down too, and there's a bunch of ways we can do it. First of all, the bigger your launcher on the ground is, the better fraction of mass you can get up into orbit because you don't have to duplicate systems to have whole bunches of little parts that you put together. If you can throw it up in big sections, it makes things a lot easier. The assembly of your big spacecraft in orbit gets easier. So, heavy lift, super important. We are not going to leave home without it. Another possibility, shown here in the right-hand corner, this is from 2001, A Space Odyssey. That ship was nuclear powered. All the stories I've been telling you about difficult propulsion systems and burns and huge amounts of fuel, those arguments become less of a problem if you can use a power source that's stronger than chemical. And nuclear could do it. Next, if we're clever about staging stuff in Mars orbit and on the surface of Mars so that we don't have to carry our entire supply throughout the entire profile that we're doing, we think we might be able to save a little mass that way. And finally, Mars has resources that we can use. It has an atmosphere, it has ice caps, it has dirt and rocks. We think we can make propellant out of some of that stuff. A lot of the weight that we're dragging to Mars and back is just the propellant that we're going to use for the very last engine burn. And if we can make that on Mars, we can save a lot of weight. And this is a picture of a prototype that we have out in Hawaii. I think it's arriving there like now. And it's going to be tested later this month to try to make oxygen from rocks. So that's an experiment that's happening right now. So these 4 things might be able to reduce the huge mass of the ship that we think we would need to go to Mars and make it back safely. So I want to change gears a little bit here. We've been talking a lot about technology and rockets, but the other interesting thing about sending humans to Mars is that it's got humans. We've sent robots to Mars all the time. We got another one arriving next month. They almost make it look easy. Of course, they never have to bring anything back. But sending people out on long missions like that has some problems that we need to solve as well. First of all, you get out of gravity, you unload your muscles. They don't have to work against gravity to move around, pick things up, and your muscles say, you don't need us, we're leaving. But we think we have a handle on that. There's good resistive exercise on the space station right now, and crews after 6 months in weightlessness are coming back in pretty good shape. I get to see the returning crew members usually a couple of days after they get back from the space station. They're in the astronaut gym starting their rehabilitation. And most of them, strength-wise, are in quite good shape despite having just spent 6 months in zero-G. Another problem is your sense of balance. It's famously known that when you get up into space, your sense of balance goes nuts and it makes you feel queasy. Almost everybody feels a little ill. About a third of people actually feel ill enough to throw up. But after a couple of days, if you don't try to do too much, it gets better. Same thing with returning. You come back to the ground, you got the spins, you feel dizzy, you feel faint, you feel weak. A couple of days, don't try to do too much. It'll get better. They don't let you drive your car for the first 3 days after you return from space. And even just walking around the hallways in the office is kind of fun on day 2 after return. You walk around and you turn a corner and whoa, they could sell this. Another thing that we have to contend with on a long-duration space mission is radiation, both from the sun and from sources in deep space, produce dangerous radiation. We don't like it. And the one thing that blocks radiation is mass, and the one thing we can't afford to launch is mass. So lead bricks, which work great on the ground for radiation protection, can't really use those in the spacecraft, they're too heavy. So maybe one possibility is you hide in your water bottles if there's a solar storm. You carry a bunch of water, you have a bunch of water containers, and inside that you build your solar storm shelter, and if there's a radiation gets high, you go hide in your water bottles. But, it might work, it might not. This is not a problem we consider to have late at this point. Another issue is bone loss. Just like your muscles, when you unload your bones, you take away the weight of your body that is always pushing on your bones. Your bones are always sensing those loads and reforming themselves in response to those loads. It's a really interesting active material. You unload them, they say, we're not needed, we're out of here. Especially in the early days when people weren't doing a lot of exercise on long duration, people came back with really bad bone loss. These days, with good resistive exercise, most people are coming back without bone loss. Of the ones that do come back with loss, most of them get it back, but there's still a small fraction of people who return from space station with a little bit of bone loss that doesn't come back once they get back under loading. So this problem, again, we're on the way to solving it, but we haven't quite licked it yet. And then finally, when you take a small group of people and isolate them in a stressful environment, sometimes they may end up being kind of unhappy. This is a possibility. We don't know what to do to fix it, but if you go back to the early part of the last century and look at polar exploration, where we had small crews isolated under horrible conditions. There was a group of people in Antarctica. They were trying to get on the ship at the end of the season to sail away before winter closed in, but the wind blew the ship offshore. They couldn't get back, and this handful of people were stranded in this little cabin on the coast of Antarctica for 2 years. And there were no murders. So it's possible to get through that, but it's hard. But again, we don't have this problem completely licked. And finally, a brand new problem that we wouldn't even have known about without the space station is some folks are coming back from the space station with damage in their eyeball, which comes from high fluid pressure inside the eyeball, which is related to high fluid pressure inside the brain and spinal column. We don't know what causes this. It's fairly serious. Some people are not able to get their full eyesight back when they return, and we don't know enough about it to be able to fix it yet. But again, we only found out about this because we had the space station. And that's a 6-month trip on the space station that can cause this. And how much worse would it have been if we'd sent somebody on an 8.5-month trip to Mars in weightlessness and had them not be able to read the checklist when they landed. So at least we found out about it, and we have a good platform for finding an answer to this one. So we've talked about the rockets. We've talked about the people. You guys should all be certified rocket scientists now. And let's go to Mars. That's all. Thank you.